Hello, my name is Aditya Singh, and in this video we will look at the solutions of second internal questions of numerical analysis and design. So the first question we have is write an algorithm for Newton forward difference interpolation. So we know that the formula for Newton forward difference interpolation is f of x is equal to y naught plus u into first order forward difference plus u into u minus 1 upon 2 factorial with the second order forward difference and so on. And in this we know that the value of u is b minus a upon h. We also call it step size. So for the algorithm, we will take the input of a number of data points, values of x naught, values of y naught, and then we will start constructing the forward difference table. First we will compute first order difference, then we will compute the second order difference, and consecutively or we can say we will continue this process until all the differences are found. Then we will input the value of x that is to be interpolated, and then we will calculate the step size h is equal to x1 minus x naught, and then we will calculate the value of u, uh, and then in the sixth step we will apply Newton's forward formula, which we have already talked about: y naught plus u into first forward difference plus u into u minus 1 upon 2 factorial into second forward difference plus u into u minus 1 into u minus 2 upon 3 factorial into third forward difference and so on. And in the next step we will compute each term and sum to get interpolated value of f of x, and then we will display the result as f of x. In second question we will write Python code for Newton divided difference interpolation formula. In this we will have two functions. The first will be divided difference table, and the second function will be Newton divided difference. So for in the first function we will have three variables x, y and n, and in this we will create a table. So fill the first column with the values, and then we will calculate the divided difference using the for loop. Then we will return the first row of coefficients, and then we will have the table for the divided differences. The next function will be to perform the interpolation, and we will have the coefficient value and x variables. So n is equal to length of coefficient, result is equal to coefficient of 0, and the product term we will start with 1 for I in range, and in product term we will have and then we will get the result. For example, input we have x, the values for x, y, and the value of n. So we will create the divided difference table, and then coefficient divided difference table x for x, y and n, interpolate for a given x in which the value is 7. So the result is equal to Newton divided difference, x coefficients and values, the second function we had, and then we will print interpolated values at x is equal to value. The third question we have is prove that the sum of Lagrange coefficient is 1. So in this we will have Lagrange interpolation formula given n plus 1 points. So the p of x is equal to summation of li x into y1 from I is equal to 0 to n, where each Lagrange basis polynomial is defined as li of x is equal to x minus xj upon xi minus xj, I plus 1, I is equal to 0 and j is equal to 1, from I is equal to 0 and j is equal to 1 to n. To prove summation of li x from I is equal to 0 to n is equal to 1 for any x. So for proof we will, let's assume we are interpolating the constant function f of x is equal to 1 for all x. Then the interpolation for polynomial should be p of x is equal to 1. Using the Lagrange form, p of x is equal to summation of lix into f of xi from I is equal to 0 to n. But since f of xi is equal to 0, that we assumed earlier, for all I, p of x is equal to summation of lix into 1 is equal to the summation of lix from I is equal to 0 to n. Therefore, the value of summation of lix from I is equal to 0 to n is equal to 1. And this proves that the sum of Lagrange coefficient is equal to 1, hence proved. So the fourth question we have is obtain Simpson's 3 by 8 rule by general quadrature formula. So the general quadrature formula is integration of f of x dx from a to b, which equals to summation of wi f of x I from in which I is equal to 0 to n, where x naught is equal to a and x naught xn is equal to b, and these are the points that are given. Wi is the weight and h is the step size, which is b minus a upon n, equally and this is equally spaced. So in Simpson's 3 by 8 rule, n is equal to 3, and which means there are 4 points. Let n is equal to 3, so the points will be x naught is equal to a, x1 is equal to a plus h, x2 is equal to a plus 2h, and x3 is equal to a plus 3h. And in this we know the value of h is equal to b minus a upon 3. So after we approximate f of x using a cubic polynomial passing through these 4 points, we then integrate that polynomial. So we will get integration of f of x dx from a to b is approximately equal to 3h by 8, and f of x plus 3 f of x1 plus 3 f of x2 plus f of x3. So this is only the Simpson's 3 by 8 rule. So this is the step by which we can have the Simpson's 3 by 8 rule from general quadrature formula. In question number 5, we have to obtain Simpson's rule from Newton-Cotes formula. So the Newton-Cotes formula that we also have seen in the previous question is the integration of f of x dx within the interval of a and b, which is approximately equal to summation of wi f xi from I is equal to 0 to n, where xi is equal to a plus ih, h is the step size is equal to b minus a upon n, and wi is the weight. So Simpson's 1 by 3 rule, in this the value of n is 2 and the points are three points we have in this. So x naught is equal to a, x1 is equal to a plus h, x2 is equal to a plus 2h also equals to b, and the value of h we will get b minus a upon 2, and then we will get the values of x naught, x1 and x2. Next, the formula will become f of x dx, which equals to a naught f of x naught plus a1 f of x1 plus a2 f of x2, where the weights ai are calculated. So a naught is equal to integration of L naught x dx from a to b, a1 is equal to integration of L1x dx in the intervals of a and b, and so on. So by integrating the weights a0, a1 and a2, we will get a0 is equal to h by 3, a1 is equal to 4h by 3 and a2 is equal to h by 3. So after substituting it into the formula, we will get f of x dx in the intervals of a and b equals to h by 3 f of x0 plus 4f f of x1 plus f of x2, which is the Simpson's 1 by 3 rule. So in the sixth question, we have to solve dy by dx is equal to 1 plus x square, which the value of y at x is equal to 0 is given 1, and we have to find the value of y at x is equal to 1 in steps of 0.5 with Euler's modified method. So we are given the function dy by dx, f of x and y is equal to 1 plus x square, value of y at x is equal to 0, and the step size, which is 0.5. So in step 1, we will find the value of y1 from x is equal to 0 to x is equal to 0.5. So value of the function we will have is 1 plus 0 square. Substituting 0 in the function, uh, we will have the value 1, and next we will calculate the value of y1, which is 1 plus 0.5 into 1, and we will have the value 1.5, and the function we will have is 0.5 and 1.5. So we will substitute in the 1 plus x square equation and get the values, and the value we are getting is 1.25. And now we will obtain the corrector value of y1, which is 1 plus 0.5 upon 2 into 1 plus 1.25, and after the calculations we will have the value 1.28125, and in the step 2 we will calculate the value of y2 from x is equal to 0.5 to x is equal to 1. So by substituting the function, we will have 0.5 as the value of x and 1.28125 as the value of y is equal to 1.25. So using the predictor formula, the value of y2 we will get is 1.28125 plus 0.625, and after the calculations we are getting 1.90625. So we will, or we can also say, after substituting it into the function, the value of function we will get is 2. So after substituting these values in the corrector formula, the value of y2 will be 1.28125 plus 0.5 upon 2 into 1.25 plus 2, and the final value after the calculations that we will get is 1.6875, and this is only the value of y at x is equal to 1. So y1 is equal to 1.6875 approximately. This is from the corrector formula. The last question we have is find the value of pi from integration of dx upon 1 plus x square from the intervals 0 to 1 using 3 points Gaussian quadrature formula. So in this, the step 1 we will have is formula over the interval -1 to 1. So the formula is integration of f of x dx from -1 to 1, which is approximately equal to summation of wi fxi, in which I is equal to 1 to 3. So we will see for I is equal to 1, 2 and 3 the value of xi and wi. So these are the values: minus 0.7746, the weight will be 5 by 9. So the xi, when it will be 0, the weight will be 8 by 9, and in the last under root 3 by 5 we will have approximately it is 0.7746, which is 5 by 9 the weight. And step 2 will be the change of interval, x is equal to b minus a upon 2 into t plus b plus a upon 2, with a is equal to 0, b is equal to 1, so the x will become 1 by 2 into t plus 1. Then dx is equal to 1 by 2 dt, so the integral will become integration of 1 upon 1 plus x square dx from 0 to 1 is equal to 1 by 2 and the integration of 1 upon 1 plus 1 by 2 into t plus 1 its whole square dt from the intervals -1 to 1. In step 3 we will apply Gaussian quadrature. F of t will become 1 upon 1 plus 1 by 2 t plus 1 whole square. So now we will compute it. So after computing we will get these values, and step 4 will be the evaluation. So the x1 is equal to 1 by 2 into minus 0.7746 plus 1, which will give 0.1127, and that's how we will calculate the values of x2 and x3, which are 0.5 and 0.8873 respectively. And now we will substitute these values in f of x, which is 1 upon 1 plus x square, and then we will compute the value of the original function. So after calculating we will get the value of pi, which is 4 into 0.7853, which equals to 3.1412. So these were the questions in the second internal examination of numerical analysis and design. In next video we will see the questions that were given in third internal examination of numerical analysis and design. Thank you.